Okay, we'll go ahead and get started again. We have two more presentations this afternoon. The first one here is Jordan Gottlieb, who is from Charter Communications, actually just right across the street, right? So he's going to talk a little bit this afternoon on some important information on MAP and MAP-T and MAP-E, right? So we'll talk a little bit about some of these transition technologies in this particular piece, and it sort of follows on this theme we've had for this afternoon, where we're talking about 6PE and now MAP and some of these other transition technologies. So Jordan's been part of communications and networking activities for about 20 some odd years now. Also a CCIE, although a little bit higher than some of the other folks in the room. Jordan is currently working on a lot of the newer technology pieces, SDN, some of these map transition technologies, and that sort of thing. So it'll be great to hear from you this afternoon. Jordan also is a first-time attendee and a first-time speaker, so we'll see if we can take it easy on him this afternoon. Jordan, thanks.
Thanks, Dan. So yeah, as a first-time speaker, I was appreciative that Chris went first and followed Tim. I also appreciated the fact that his topic and the questions at the end lead in really well into my presentation, which is mapping of address and port. So there we go. Here's a quick agenda. I'm first going to give introduction to MAP, just to give you a sense of what it is and what it's solving. Look at some of the benefits. I hate to introduce a whole lot of terminology because I think digesting it is really tough. So I'm going to try to walk you through some essentially packet walks and provisioning scenarios. So some of the terminology that I give you guys initially will make more sense. I also think MAP is really interesting to me because, and again, it follows up a lot on the discussions that have been held earlier, the flexibility in what you can actually carry in an IPv6 prefix, given that you're not worried about being really efficient with your address assignment. So the algorithms used in MAP make use of this. This is one of the core constructs. And lastly, I've been working on this for about a year. I want to cover the considerations because MAP has some pretty nifty features, and it solves some problems for providers like the one that I work for, and maybe even for some of these campus networks. It might be an application there as well. But there are definitely things that you need to consider before you dive in. And lastly, I have a list of resources and attributions that you guys can use if you're interested in the topic and want to research further. So what is MAP? Well, it's kind of the reverse of the presentation that just came up. Rather than pushing IPv6 out and having IPv6 operate on the edges, we're going to turn that around and we're going to push IPv4 out in the edges. So we are going to use, it provides for access from a customer or client IPv4 domain through an IPv6 network, IPv6 domain, and then out to another IPv4 domain. And in most cases, that's going to be the internet. Now, the primary application from my perspective, and I think many of the people that are looking at it, it's N2N IPv4 address sharing. That is, assigning multiple customers to a single IPv4 address. It's a competing technology to some of the technologies that have been mentioned earlier, NAT 444, DS Lite, Lightweight 4/6, 4RD. Am I missing any? I think I got them all there, or close. In the sense that it allows your customer network to still have their RFC 1918 addressing, their typical RFC 1819 addressing allows them to be autonomous in management of that and still share a public IP address with other customers. How we get across the IPv6 network is defined by two transport modes in MAP. You've got MAPE, where we take the IPv4 traffic and we encapsulate it in an IPv6 header. The other transport mode is MAPT, which is mapping of address and translation using translation. So rather than encapsulating the traffic in IPv6, you take the IPv4 header and you translate it to an IPv6 header. To us at Charter, and for me, one of the things that's really attractive with MAP and what sets it apart with a lot of the other from a lot of the other transition technologies is that it's extremely complementary to native IPv6 deployments. As I take you through the presentation, you'll see that a MAP network looks a lot like a native IPv6 deployment. There's very small nuances and deltas to how you provision and operate a MAP network. So just to give you a quick overview of the different components that make up a MAP network, we've got the two devices that are necessary. This is one of the deltas. We've got a MAP customer edge device, and this is typically your home gateway. It's something that you would pick up at Best Buy and drop behind your cable modem, or it could be your DSL router. And that's responsible for taking the IPv4 traffic at the customer prem and either encapsulating it or translating it for transport over the IPv6 network. Now, if you notice here, I have an IPv6 network on the LAN side behind the MAPCE. And the reason for that is natively, and this is, again, I'm going to keep hammering it home, you have a native IPv6 prefix on the LAN side in MAP deployments if you address things properly and you accommodate the forwarding. The other hardware piece is the border relay, or BR, and it is the terminating side of any MAP deployment. It can be, in some cases, it can be an existing piece of equipment that's been upgraded to support MAP. And in other cases, it might be a dedicated appliance that supports MAP, and for that matter, might support other transition technologies that you might want to run concurrently. I'm trying to make A10 happy here. So MAP deployments are made up of MAP domains. You could deploy it as a single MAP domain, but as I'll show later on the presentation, that might not be the best idea. MAP domains share a common set of parameters, and I'm going to give you some of the basic ones. We have a rule IPv6 prefix, and you have to think of it as the prefix, the parent prefix from which all other prefixes are delegated for the purposes of MAP. Now, that being said, that can be the same parent prefix that you're allocating to non-MAP customers. Doesn't have to be unique to MAP. Then you have your rule IPv4 prefix. And this prefix, think of it as your NAT pool. Those of you who have configured firewalls and do overload or one-to-one, and you have to allocate a NAT pool, your IPv4 rule IPv4 prefix for a particular MAP domain is your NAT pool. Now, your embedded address, this is a value within your IPv6 prefix that you allocate. This is a set of bits that are interpreted from your allocated prefix on the customer side, on the prefix that's allocated to the customer, that actually do the representation for an index into the address that they should use and the set of ports that they should use. And I will go into that later in detail. And lastly is the BR address or prefix. I mentioned before, in order to get to the external IPv4 domain, the internet, the old internet, I'll call it, since somebody said the internet is now officially IPv6, is reached through either a BR address, which is the case of MAPE, because you're encapsulating and you need an address that you're sending your encapsulated traffic to, or a prefix, in the case of MAPT, because you're doing the translation and you need enough space to embed the destination address that you're trying to reach as part of the translation process. Now again, I'll have visuals for that later on in the presentation. So one of the interesting things and one of the attractive things for me about MAP is it seems like there should be a control plane between the CPE and the BR, but there isn't one. MAP operates on the notion of shared rules and shared algorithms. And these are some of the rules. You have your base mapping rule, the stateless rules, correct? You have your base mapping rule, and that allows, for instance, the CE to determine, based on the prefix that it was delegated, what is its public IP address? What is the set of ports that it should use? We've got our FMR or forward mapping rule, and that is a special case. And honestly, even one of these days I have to send out a message to the IETF mailing list. But I think that's one part in the spec, in the draft right now, they're very sparse on. But in the mode where you go in a more mesh mode where you're not necessarily sending all your traffic to the BR, where you want CE to CE communication, you would employ FMRs. And then lastly is the default mapping rule. Now technically speaking, DMRs are only defined for MAPT, but it's essentially the same. We have the same sort of functionality with MAPE with the BR address. I put in this slide because there's a lot of confusion, especially for people that are first broaching the subject about how all the addresses fit in, especially from the CE standpoint, and what addressing you can use. So I put in this slide. When you provision a map CE, you're going to give it a prefix for allocation on the LAN side. The WAN interface, actually, the interface that faces whatever your northbound layer 3 device is, that doesn't really have any relations to map. It's just a interface where you can layer 3 forward through. And that's a key concept. All traffic that is map traffic gets originated from an address called the MAP IPv6 address. And that address is just a host address out of your prefix allocation. It's simply a /128 out of there. So, and has a very specific addressing format, as you'll see later on in this presentation. The customer prefix, the IPv4 prefix, just like it is today. You go out to Best Buy, Staples, not to keep pushing Best Buy on you guys, Office Depot, what have you, Walmart, you pick up your router, you can address the LAN side any way you want. Same goes with MAP. All right, so this is what makes MAP this slide. And it goes back to the concept, some of the things that we've been discussing before, which is taking certain bits out of the v6 prefix because we can be loosey-goosey with it, right? And using them for an application. And this is even for those of you who aren't working for a service provider where this is probably most applicable. It might kind of give you some ideas, and maybe there's some other ways I can use these bits, right? Algorithmically, to be able to automate something. So I thought this was pretty nifty. So the core concept here for the EA bits is essentially when you define your domain parameters, it lets you know which bits you should interpret as your EA bits. And based on, in this particular example, how big your IPv4 rule set is, rule prefix is, which in our case is a /24, you'll also know what bits are left over to represent unique port sets. So in our particular case, we defined an EA length of 14. That was a definition that was configured or defined, I'm sorry to repeat myself there, as part of the domain attributes. And we defined it at 14. The fact that our IPv4 rule prefix is a /24, which is represented by 8 bits, leaves us 6 bits to do unique port set allocations, right? And 6 bits, how many values can it represent? 64, right? So we have, for this particular map domain definition, we have the ability for customers to, we have the ability to allocate 256, right, unique addresses, and then 64 unique set of ports. And I'm going to go through a practical example in the algorithm section. So what are the benefits of MAP? I kind of alluded to this before, but it really looks a lot like what we have at home today. All right? You've got your router. It's running NAPT. You're not breaking UPnP like you are with some other transition technologies requiring other control protocols to be able to support it. If you want to do manual port redirection, you can still do it. Now, you can't do it on whatever port you want. You have to do it on the ports that you've been assigned, but you could still do it. You get less ports, right? In this particular case, you have 1,008 ports for each one of these PSIDs, but it looks and smells just like the broadband deployments that we were familiar with. And because you're using IPv6 addressing, this is a really important point, and this is a big sell for me against NAP 444. You're not using RFC 6598 addressing. You're not forced to use something like that. And the reason it's difficult for large organizations to do that is actually a /10 is not a whole lot when you look at how we allocate address space. And so the ability to decouple that is really, really helpful. Stateless border relays. We had somebody nail it, right, earlier on today, the stateless component of MAP. Border relays behave more like routers and less like firewalls. Working for a service provider, I don't want to stick firewalls in the middle of my network. I want to be able to have devices behave more like routers that are just basically forwarding based on bits that they're seeing in the v6 address. I don't want them to keep states, be vulnerable to attacks because of states. I want to be able to pass traffic in asymmetrical fashion, right? I don't want to care if my traffic went out 1 BR and comes back in another BR. I don't want to worry about having to replicate state between the BRs for high availability. If one BR falls out, one of the things I can do with this technology is I can anycast either the BR address or the BR prefix into my network. If one BR falls out, the traffic, your routing protocol will take care of dragging the traffic over to an alternate BR, and it will forward it on. And from an engineer at a service provider perspective, what I love is also how simple it is to test. I don't have to have stateful testers. I don't have to have a tester that needs to validate proxies and ALGs, right? I'm just passing unidirectional traffic and seeing if it does it accurately, if it does the translation accurately, and that it doesn't fall on the floor. One last point is also equal cost multipath. If your platform supports that next hop and you have multiple BRs connected to a single device, it scales very well horizontally from that perspective as well. All right, minimal logging requirements. So with a lot of other CGN technologies, there's varying degrees of logging overhead. Built into MAPE, since it's all algorithmic, you really don't have any additional logging requirements beyond your initial provisioning system. So non-shared public IPv4 addresses can be mapped back to the assigned IPv6 end user prefix by simply providing the IPv4 address in a case where you're not doing end-to-one address sharing. And shared public IPv4 addresses now require, like every other CGN technology, any sort of other overload technology, you're going to have an IP address and port combination, right? But the nice thing is we don't have to go back to some table or some log, other than the DHCP log, which we'd have to go in from the service provider perspective in any case, to figure out who the end user is. We can do this algorithmically. And if you're interested, if you want to see what happens when a network engineer gets bored and starts writing Python, you can check out my project here on GitHub. And I wrote a Python 3 library that allows you to do a lot of the map calculations. And I wrote this script that's in the examples directory that shows you some of these for the purposes of either an abuse complaint, right, or a law enforcement request. They come back with a public IP address and port, and you want to map it back to a customer, pipe it through this script. Somebody would obviously make a much more elegant interface than this. And you get back the delegated prefix. You go back to the DHCP server and figure out who had that delegated prefix at that point in time. And now you have who the offender is. All right, maybe I'm beating a dead horse here a little bit, but it aligns really, really well with native IPv6 deployment. It's really just a IPv6 deployment with prefix delegation with some very minor deltas from my perspective. A piece of equipment at the customer edge and enhancement or a new piece of equipment within the provider network. We don't have to, beyond that, we don't have to assign it any sort of unique addressing. We can use our existing aggregation for our native IPv6 deployments. So now I'm going to actually take you through some of the packet walks. All these packet walks here are based on this particular map definition. For some reason, actually I can tell you the exact reason, I didn't do things on nibble boundaries. And so it's a little bit harder to read. But the reason for that is because my test cases, I didn't want to do them on nibble boundaries because I wanted to make them harder. And I kept it in the presentation, which in retrospect was, I probably should have changed. But so we have a prefix, a /62 that's delegated to our customers. This is one particular prefix. We have our rule IPv6 prefix, our rule IPv4 prefix, our EA length of 14, and the PSID of 58, that's actually derived from our PD. So this is not something that we assign them. I was working with one of our vendors to try to get them through MAP, and I was looking at a capture of DHCP v6 session, and I'm looking in there, I'm like, wait a second, you're assigning the PSID. And so I pointed them over to the draft document for DHCP software support and clarified that. But that PSID is not actually assigned in the DHCP by any DHCP option. It's derived from the PD. So I'm going to show you an example, a very simple example of the DHCP v6 provisioning example, a MAPE traffic flow example, and one for MAPT. I told you before, here's more of the beating of dead horse. It's almost identical to a native IPv6 deployment, right? I can do like hybrid, where the home gateway address allocation is through Slack, and then I do a PD allocation for the network behind, and then I just tag along just option 94 and 95. That's the only difference. Right? If I took away option 94 and 95, that would be essentially, if you also take away the ability to do RFC 1918 behind the home gateway, that would just be a native DHCP v6 prefix delegated environment. The only difference is option 94 and 95. And all you really have in option 94 and 95 are the rule IPv4 and IPv6 prefix, the EA length, and the PSID offset. And I'll go into that in a little bit more detail later on. And lastly, either the BR address or BR prefix for the particular domain. That's all that's in option 94 or 95, and it's for each domain, so you don't have to do it per customer, right? This is something that is akin to an NTP server setting or DNS server, right? All right, let's jump into our example here. So we have a typical customer network with the RFC 1918 address network. I also show that they have native IPv6 support. If you look, I have kind of a forwarding timeline that matches up with the packet coloring. So I'll do the IPv6 case. You know why? Because it's really easy. If you have a client on your home network that's IPv6 address and has an IPv6 transaction to do it out to the internet, you just forward it native IPv6. Nothing happens. It just forwards along its merry way through your network out to the IPv6 internet. Now in the MAP case, if you have IPv4 traffic, just like today, client generates source 192.168.1.101, destination 206.1.1.1.1, pushes it out to his default gateway. The router grabs it. Now the first thing it's going to do is it is going to do the NAPT function. The only difference between the NAPT function that it does in this particular scenario and what you see in your home networks today is it operates on its restricted port set, right? It is only allowed to NAPT using the ports that it was allocated. In the case of where you don't actually have any bits allocated, I want to keep mentioning the fact that you don't actually have to run NAPT on that device, but this is where for us we get a whole lot of bang for our buck. So this is actually a case where IPv6 may make you money. So we do the NAPT function internally on the router. So you're actually translating to your public address at the customer prem, right? So again, this is in support of things like UPnP, your manual port redirection. You know what your public address is. You don't have an intermediary network like RFC 6598 to deal with. You actually know your public IP address at that point. In the case of MAP here now, what do? We then slap on an IPv6 header, right? The destination is just going to be the BR. The source is the special MAP address, right? And within that MAP address, I'm going to point out two things that are embedded. The first is your source public IP address. So if you look in there, 44.72.202 is your public IP address of 68.114.2.2. The other thing that's in there is actually your PSID at the end there, which is 3A, which is equal to 58. Right? Why do we need that? Why is that useful? Well, when it gets to the BR can then validate to make sure that you're not using any ports that are out of your range. And lastly, the BR gets it, pulls off the IPv6 header. In the case of E, it just forwards it along. I left off the other direction on purpose because in order to understand how the opposite direction works, you actually have to understand how PSIDs are how the set of ports are calculated for a particular PSID. Once you can calculate that, you'll know what your PSID is, and it's very easy to build the address to get it back to the proper CPE again. MAPT is identical for the first two steps, and then things change. We go from the encapsulation mode to the translation mode. So this time, rather than sending it to a specific BR address, we take the destination address of 206.1.1.1 and we stuff it into the IPv6 prefix destination, right? If you look in there, 206.1.1.1 is represented by CE 10101. Right? It's actually embedded in that address so that when the BR gets it, it knows who he's sending it to, right? The TCP header in this particular case remains the same, right, post NAPT. The source address is exactly what we did in MAPE and for the exact same reasons, right? We want to be able to, once it gets to the BR, you want to be able to validate that the PSID and the ports match up. This is my favorite part. This is the actual algorithms. Not that they're that tough. They're actually quite simple. So let's look at the base mapping rule and how that's calculated. So we have our rule IPv6 prefix. Once you get beyond the rule IPv6 prefix, you're going to hit your EA bits. How do you know, again, which bits to use? And so I've expanded the EA bits out into binary so we can make some sense of them. So how do we know what address to use and what PSID I should use? Well, it's simple. Given our PD allocation of 2001, 506, 101, 2E8/62, and the rule IPv6 prefix, we go to the end of the rule IPv6 prefix, and now we have 14 bits that define the EA bits. We know that we are trying to represent a /24, as I mentioned before. So we know the first 8 bits is going to be an index into the IPv4 address that we're going to use. Since we're using 68.114.2.0/24, index value 2 is 68.114.2.2. Now the CPE knows what address that they should be using for their public IP address. How do we know what ports we should use? Well, we know our EA length was 14. We know we used up 8 bits for our address index. We have 6 bits left over. Look at those next 6 bits. There's our value, 58. So every customer, so you're not having to teach your DHCP server how to sling PSIDs, all he needs to know is how to sling prefixes, right? Just do your prefix delegations, right? And that will imply the PSID that you get and allow you to calculate it. Once you have your PSID, how do we know what ports we need to use? This is where PSID offset comes into play. So, you know, I should be ashamed of myself because I was good about using A and M, and then I invented my own Y. So A and M are actually in the IETF document. I put in Y because PSID wouldn't fit, and it was too late for me to change it. I want to say it's capital K, but here we have 16-bit representation of all possible ports that we can use, right? And what we do is we take our, whatever the defined PSID offset is, which is 6 bits, and offset off that, we take whatever amount of bits were left over, which in our case were 6 bits for the PSID. We overlay it there, and then we have our M bits left over, and I'll explain what those do in a second. Now, when we look to figure out what ports we're allowed to use, all we have to do is Y is a fixed value in this particular context, and it's within the context of the full 16-bit address. Whereas the 58 value is only evaluated within the context of those 6 bits. When you're actually trying to figure out what ports ought to be are allowed to be used, you have to do it in the context of the 16 bits. So we have that value fixed at 928. With a PSID offset of 6, we at least have to have that first bit lit in the A bits, right? And then M can be any combination of values for those 4 bits. And that is what allows you to figure out what ports you can use. Now, going back to the example of traffic coming back into the BR, all you have to do is take that port value that you're seeing coming in for a particular address, overlay it on these 16 bits here, look at the bits that represent the PSID, and now you know which PSID it's associated with, right? So that's how that mapping occurs going back in the other direction. And then you have obviously the address index component as well to remap it in when you're rewriting the address for things to go back in the other direction. So in this example here, what I did was essentially, here's a simple case. How do we figure out what the first usable address is? And how do we figure out what the last usable address is? If we look at the first usable address, the A bits, the first bit has to be lit, right? We can't have all zeros in the A bits, so we have a value of 1024. 928 is the fixed value for our PSID. And then M, because we can't have any value there, is set to 0. If we add those all up, first usable, for this particular map domain definition, the first usable port is 1952 for this particular customer. Second one is M with the first bit lit up, right? So it's 1953. If we light up all bits, all the A bits, we get 64512. Add the 928 to it, then light up all the M bits. Now we get the last possible port that we can use. And if you do the calculation here, this particular customer, given this kind of domain definition, will have 1,008 usable ports. They're not sequential, right? They're 63 ranges of 16 addresses. Deployment considerations. All right, I lied to you. I fibbed. The border relays are not 100% stateless. Why? Well, we have the fragmentation case, right? Your initial fragment is going to have the port value. The ones that follow aren't. How are you going to pass it to the right? How are you going to do the translation? Well, guess what? You're punting it to the control plane. And you're going to have to track the fragment ID and associate it with the proper MAP address that you want to send it to. Payload considerations. Somebody talked about overhead. You know, all this fancy schmancy features, they come with a cost, right? We have some costs here. And again, my solution is the same as Chris's, right? And as a service provider, we've been thinking about this for a long time, right? We run MPLS at the core. We're providing all these VPN technologies for our customers. So we have jumbo frame support. Where we don't quite have it yet in some situations is at the customer edge. But ideally, as for instance with DOCSIS 3.1, we'll get a bigger payload in the case of us, a cable provider. So we'll be able to have a jumbo frame support on the WAN side. Hopefully we can also get it on the routers that we're getting from our home router vendors as well. And now, as long as we keep the MTU to 1500 facing the customers won't be able to tell the difference between the service they get today and the service that they would get from a perspective of a payload, from a payload perspective, service they get today and the service they will get potentially with MAP. Layer 3 transparency. This was an interesting discussion on the Softwire email threads, mailing list, excuse me. And this is one of the big differentiators between MAPE and MAPT. MAPE achieves full transparency, and transparency being all the values in the IPv4 headers, making it across from the CE to the BR or vice versa, right, during the translation or encapsulation process. In the case of MAPE, since we're just encapsulating, you have full transparency. In the case of T, since you're doing translation, you don't have full transparency. And the specific case, probably the most interesting case, and I'd be interested to see if I can get any feedback here, is in the case of DF and MF flags, right? So RFC 6145 describes how the stateless translation should occur in MAPT. And the way it does PMTU discovery, the way it translates the DF and MF bits is if you have a DF bit, if you have a DF bit of 1, right? If you have don't fragment on, then you don't have a fragment header when you craft your IPv6 packet. If DF bit equals 0, then you have a fragment header whether or not you're actually fragmenting. Well, what happens if you're fragmenting and you want to set your DF bit to 1? There's no way to handle those combinations. And that's recommended in RFC 4821. There's a little bit of a flame war going on back and forth, and at the end there was sort of a concession by those who were concerned with this and sort of got them to admit that this was very much a corner case. I'm really interested to hear from anybody here of cases where they think that this would be a showstopper. I've had, given our initial testing for the types of applications we anticipate people using, I've had a hard time hitting this corner case. Rule IPv6 sizing. So this is really interesting. This is actually, it kind of follows up in some of the discussions that Infoblox and BT had about planning. You can't just deploy this willy-nilly. Because if you're not careful, the first instinct, and it was the first instinct I had, was to think to myself, you know what? I'll just deploy one map domain at a top aggregation level at my 32 boundary, and I'll drive map from up there. I sat down and did the calculation, and I did, this is not necessarily how we would lay things out, but see, if I allocate the end users a /62 and I want to go 64:1 ratio, then I'll need a /7 of contiguous IPv4 space. Does anybody here have a maybe Verizon? Verizon, you guys have a /7? Contiguous? Does anybody have a /7? So, okay, so that was a little humbling, right? And so when you deploy MAP, you really have to think about how you lay things out, how you do your sharing ratios, what you're going to allocate your customers in terms of IPv6 prefix, and where you do it, so that you can have something more manageable. So I give an example here of something that would generate a /22 deployment, right? And for a service provider, /22 is very doable. We have lots of contiguous /22 blocks. MAP-E or MAP-T? I like MAP-T. And actually, again, Dan served it up for me today, I got to tell you. So, one of the questions about visibility and troubleshooting, the thing I like about MAP-T is the fact that you have full 5-tuple visibility, right? And so that if you want to set your edge filters, you can set them in the edge, you can set them deeper in, you can have your DPI platform look at things. They don't have to understand that the stuff that the real meat is behind a layer of encapsulation. So you can do your QoS, you can do your edge filters. There's the opportunity for traffic engineering outside the MAP domain. What do I mean by that? Well, the natural tendency in the hub and spoke model is to always send it, not the natural tendency, the operational fact is that you're going to send it to a single BR. At best, you're going to ECMP across a set of BRs that are connected to one device. What if you have an arrangement with another provider or organization where instead of sending it here, you want to send it here, right? Because you're not just sending it to a BR address, there's the opportunity to play some games with BGP and do a little bit of traffic engineering to send it to an alternate location. Just send a more specific BR prefix route. The ability to deploy, this is a mouthful. Let me just put it in plain English. You can put IPv6 networks, IPv6 servers on your IPv6 networks and access them from your IPv4 hosts natively. So in our case, let's say we want to deploy a CDN, we only want to address the server's IPv6. We can get them, accessing them directly without having to hit the BR. Superior levels of granular for link aggregation. And lastly, denial of service countermeasures, such as feeding in BGP flow spec rules for, let's say you have a customer who's infected with a virus and we want to do certain forwarding behavior, let's say through a cleansing farm or something, somewhere to clean up this traffic. We can push down BGP flow spec, right, down to a device that's very close to the customer and do alternate forwarding behavior for them. You can't do that with E. Done. Don't have officially a question slide, but I'm glad to take any questions. I put links to all the resources. The first and third are really interesting as they provide you links if you're interested in setting up your own environment.
So I will admit that this is probably a better Band-Aid than the other Band-Aids we've put together to preserve v4 live support. But I got to wonder, all of these Band-Aids come with a cost. This one seems to come with the cost of providing your customers very long v6 prefixes, which most people in this room know I don't advocate. 48s are good.
It would be advantageous to actually give them a 48. It would actually ease my case of what my v4 prefix allocation is. So it would actually reduce what I would need there. This was some test cases that I was using. By no means am I advocating a /62. We're probably,
Fair enough. It also comes with the cost of hardware and people and maintenance and phone calls and call support centers and whatnot. How long before the various eyeball service providers start actually passing that cost along to the customers in the form of a v4 surcharge if you want to keep using v4?
I can't answer that question since we're just on the access side. But what I can tell you is one of my hopes is that some of the limitations that you have with these transition technologies, especially ones that roll out native v6, will actually drive the providers of content to start doing v6 content, right? Because they'll start getting all these calls that this broke, that broke. But by the way, a lot of these people are using this transition technology or and they have v6 available where, you're doing end-to-end transport like as we intended it, as it was initially intended, without these layers of translation. So I'm actually hoping that this is a force that will actually drive the content providers to go v6.
Have you considered how you're going to unravel this when you're a v6 only environment?
That's the beauty. I just shut off that DHCP option. That's what I'm saying. This is like all the effort that you're putting in. There's incredible amount of overlap for a native IPv6 deployment. All you do is shut down the option. That's it. And now you've got a native prefix delegated environment. What was that? Yeah. I mean, BRs at that point will be useless anyway, but yes, you'll want to deprovision your BRs.
So one of the key components of this is the consumer gateway. And that's the one that's got to do some NAT 4.6 or the conversion. Mm-hmm. So what's the vendor uptake on providing that function on these Best Buy Staples Office Max gateways?
Let's just say there's a lot of encouraging news. I don't think I can go beyond that.
Understood.
But
thanks.
Names that you would recognize.
Okay.
If only that were true. All right, thank you.
Good.